Okay, so let's have a look at the Leaving Certificate Higher Level Maths Paper 2 for 2018, and we're going to have a look at question 3. So we have a security code, and it consists of 6 digits chosen at random from digits 0 to 9. The code may begin with 0 and digits may be repeated. So for example, we can have 071737. How many of the possible codes will end in 0? Well, here I have 1, 2, 3, 4, 5, 6 of our boxes here, and we know that we must end in 0. So our last digit must be 0. So there is only one possibility for our last digit. So what about our first digit then? Well, we can repeat digits, so we have 10 possibilities for our first one. Because we can repeat, we also have 10 possibilities for our second one, third one, fourth one, and fifth one. So if we multiply all these out here, we get 10 to the power of 5, 1, 2, 3, 4, 5, or just 10, 1, 2, 3, 4, 5. So we have 100,000 here. So there are 100,000 possibilities. Okay, so what about part 2? Find how many of the possible codes will contain the digits 2018 together and in this order. So in this particular case we have 4 digits, so there are 2 other digits that we need to choose from. Now we can have the first digit, or the first let's say the first section of our code will be 2018. So the first section of our code will be 2018. There's only one possibility for that. Now the other 2 digits, the remaining we remember we have 4 digits in here, and there's only one possibility. We have 10 possibilities then for our 5th digit, and we have 10 possibilities for our 6th digits. This is one possibility. Now the other possibility is, and remember this is this arrangement here, or this is the word or here, which means we add. So we could have something like this. Again, we have 3 boxes here. We could have our 4-digit number here, 2018, in the middle. So we could have only one possibility here, which means we have 10 possibilities for our first digit, and we have 10 possibilities for our last digit, but we have only one possibility for the middle 4. Or again, the other possibility, so that's plus again. So we have our 3 boxes again multiplied. So we could put these 4 digits out at the end here, so we've only got one possibility for our last 4 digits. So we have 10 possibilities for our first digit, 10 possibilities for our second digit, and then only one possibility for our last 4 digits. So this is going to be 10 times 10, which is 100, plus 10 times 10 here times 1, which is 100, plus 10 times 10 times 10, which is 100 here. So our answer here is 300. So we can have 300 possible combinations in this particular case. So this is our answer here. Okay, so let's have a look at part B then. Part B is where we have to find A, B, C, and D if n plus 3 factorial times n plus 2 factorial divided by n plus 1 factorial times n plus 1 factorial is equal to this cubic expression here, an cubed plus bn squared plus cn plus d. And A, B, C, and D are natural numbers, so they're whole numbers, positive whole numbers. Okay, so let's see if we can work this out. We have n plus 3 factorial times n plus 2 factorial divided by n plus 1 factorial times n plus 1 factorial here. Let's put the right hand side in as well, and we'll work it down. So we've got an cubed plus bn squared plus cn plus d. So really what we've got to do is work out the left hand side, make it look like the right hand side, and then equate the coefficients. So let's just expand out the left hand side here. Now I can see here on the bottom I've got an n plus 1 factorial and an n plus 1 factorial. So what I'm going to do is bring this one here and this one here down to n plus 1 factorial so that I can cancel these two, or divide them if you like. So So for example, if you have 3 factorial, that just means 3 times 2 times 1, by the way. So if you have n plus 1 factorial, or n plus, let's say n plus 3 factorial, that's just going to be n plus 3 times n plus 2 plus, or sorry, times I should say, n plus 1 factorial, or n plus 3 times n plus 2 times n plus 1, and so on and so on and so on. So I'm just going to take the n plus 3 here, and I'm going to write it as n plus 3 factorial, write it as n plus 3 times the next one less, which is n plus 2, times the next one, which is n plus 1. And I'm going to leave that as n plus 1 factorial, because this will keep going down to 1. Now n plus 2 factorial then is just going to be n plus 2 times n plus 1 factorial. And I've only gone down as far as n plus 1 factorial because I have these two on the bottom here. That's all over n plus 1 factorial times n plus 1 factorial. And that's equal to all of this here, an cubed plus bn squared plus cn plus d. Now, you can see here why I stopped at n plus 1 factorial here and here, because everything on the top is multiplied, everything on the bottom is multiplied, so I can divide this by this, I can divide this n plus 1 factorial by this, and you can see now that I'm left with these three brackets, n plus 3 times n plus 2 times n plus 2, that's this one, and this one here, multiplied, and that's going to be equal to an cubed plus bn squared plus cn plus d. Now all I've got to do is multiply these three out. So if I multiply the first two out, I get n squared plus 3n plus 2n is 5n plus 2 3 6. Okay, and that's multiplied by n plus 2, and that's equal to this here. Now multiply these two out, so what I end up with here is n cubed, multiply these two, 7n squared, because I have, let's see, well, I'll multiply it out, I'll write it all out. I've got an n cubed, I've got 2n squared, so I'm multiplying 2 by n squared, so it's 2n squared. Now I've got this 5n times this n here, so that's going to be 5n squared, so you can see where I got the 7n squared earlier. Now I've got this 5n times 2, so that's going to be 10n. And I've got 6 times n, which is 6n. I've got 6 times 2 then, which is 12, and again that's equal to this bit here. Let's just simplify that. We've got n cubed, we've got 2n squared plus 5n squared, which is 7n squared. I've got 10n plus 6n, which is 16n. I have a 12 here, and that's equal to an cubed plus bn squared plus cn plus d. Now we're really down to bare minimum here. We've simplified the left hand side as much as we can. Now if you look at the coefficients here, you can see that we have a 1 here, we have an a here, so we can see here that a is going to be equal to 1. Now we have a 7 here in front of the n squared, and we have a b here, both plus, so we have b then is going to be equal to 7. The coefficient of the n here is plus 16, and we have a plus c here, so we can see here that c is going to be plus 16. And then our d here is the term independent of n here, so it's just going to be d is equal to 12. And that's it. That's our answer to part B, and in fact that's the end of question 3.